All right, everyone, let's get started. So Friday we have a midterm. Do you guys have any questions about anything regarding the midterm? No?
It's in class, right?
Yeah, it's in this room, regular class time.
What do
Yes.
the grades typically look like for the first midterm?
What do the grades look like?
Yeah.
I don't give grades, I just give percentages or
Yeah,
points.
what are the percentage?
I guess it can vary depending on the students that term and the exam that term. So sometimes, maybe in typical would be like 60% average, but it can be lower, it can be higher. Something to keep in mind is there's a lot of different ways to earn points in this class. You have midterms, 20% of your total grade, then you have homework, 20%, lab, 20%, quizzes, 20%, final project, 20%. So even if you do really bad on one of those 5 chunks, you still have the other 4 to do well on, right? So there's a lot of different ways to earn points. So keep that in mind. Invariably, there's always some subset of people who doesn't do well in the midterm. So I know that's going to happen again. So don't panic. You also have the chance to do better for the next midterm if you didn't do as well as you'd like on the first one. The midterms are a little bit more mathematical. Some people feel much more comfortable with the coding parts of this course and less with the math. So those who feel more comfortable with the math have a better chance of doing well on the midterm. That's just how the midterms are. I think it's important to test that ability. I do think that's an important ability, but it's not the only important ability. I think it's also important to be able to code and understand things. So, all right. Any other questions? Yeah.
Could you just remind us, is it 1 page of notes and no calculator?
That's right. 1 page of notes you can write on both sides of a piece of paper, and no calculator, no phones, no electronic things. The way that I see the goal of that sheet of notes is, number one, obviously, you probably can't just memorize everything in the notes, so it's useful to have that. But I find even more important is the process of making that note sheet. Is when you go through the notes and you write down what is important, it has a way of distilling everything down in your mind, so that because now you're in a position to sort of understand what we did over those first 4 units. When you're going through them one by one, it's hard to get the big picture in mind. Now you have that.
Is there anything that we're not allowed to put on the note sheet?
You're allowed to put anything on there. So what I have seen sometimes in the past is like students reducing the notes down to tiny little squares, and that's why I said handwritten rather than like photocopied down, because I don't think that's actually an advantage to have all the notes there, because then you find yourself like trying to look through and find things, and it just wastes time. So you want to get all that information in your head, not on the note sheet. And by going through the notes and choosing carefully what to write down, it helps to solidify things in your head. So yeah. So I would say that's probably, yeah. I don't have any particular restrictions on what you put there. All right, any other questions? Okay. So in spirit, it will be, similar to the practice midterm. I do like to have some stuff on maximum likelihood estimation, unbiasedness, as well as some simpler questions from the first couple units. That's usually what I have. Okay. All right. Okay, so we have been going through Unit 6. Unit 6 is all about optimization and trying to understand when we get this complicated loss function, how do we actually minimize it? How do we find the parameters of our model? And for that, the first thing to understand is gradients. So on one hand, we have the definition of gradient. So it's basically a vector of partial derivatives. So when we have a model that depends on a vector of parameters w, the gradient is just a vector of all the partial derivatives with respect to all the different components in our parameter vector w. When that w becomes a matrix, then this gradient becomes a matrix of all the partial derivatives. This has exactly the same dimensions as the W itself. Okay. And then in terms of interpretation, important things are the gradient equals 0 at the minimizer. Usually our objective is to find the minimizer, so in some cases we can figure that out by solving for the W hat for which this expression gives us a 0. It's not always possible, but in a lot of simple problems, the kind you find on the homework, on the exams, you can do this. In terms of other interpretations, the gradient tells us the direction and the slope of the maximum increase, like steepest direction uphill. So if you're sitting on this surface, so this surface here, this is a minimum, and you want to go uphill. Okay, if you're exactly at the minimum, you're at this flat spot, and there is no direction that takes you uphill. But if you move a tiny bit apart, a tiny bit away from that minimum, like to the right, then the gradient vector tells you to move this way. This is your steepest way uphill. On the other hand, if you were up here, steepest way uphill is probably this way. And the gradient, the length of that vector, the norm, tells you how steep it is. Okay, so those are the main interpretations of the gradient. We saw how to compute it using some simple examples, how to code it. And then we started talking about using the gradient to approximate functions linearly. So the first thing is we said, okay, let's look at scalar input functions, the simplest case. So we have a function j of a scalar w. And we said if you want to write the Taylor series of this at some point w naught, it has a form where you have the j at w naught, then you have the slope at w naught times the deviation from w naught, and then there's all these higher order terms of the Taylor series, but we're not really interested in getting all those details. We just want to summarize them and say, basically, when this little deviation is small, all those terms are dominated by the quadratic term, and that we express that using this big O notation. And basically, you can think about this. When we say a function is order epsilon squared, it means that function is at most a constant times epsilon squared when epsilon is close to 0. So we'll use that a couple times. So this is inequality. This is the exact Taylor series. Now, what we often want to do is we have this function. We want to just approximate it at this in the neighborhood of w naught. And we're going to go for a linear approximation. Just approximating that function by a line. It has to equal the function at exactly omega naught. So at that, this red approximation exactly equals this at omega naught. And then it's linear. And so we should set the slope of our approximation equal to the slope of the function at omega naught. So that's what we do here. Essentially just dropping all the higher order terms. So that gives us the match of the functions and its approximation here, and this gives us a match in slope at that same point. And often this is a good enough approximation in a small neighborhood around here for us to simplify things and derive things tractably without getting distracted by all these higher order terms. Okay, any questions on first order approximation? Okay, so we did it first in a scalar case, and then essentially in the vector case, it's the same idea except that the linear term is basically a sum over all the individual partial derivatives and all the individual perturbations. But then what we figured out is you can rewrite this as the inner product of the gradient vector and the perturbation vector. So it's just another way of writing it that is more concise and in some ways more intuitive if you know about inner products. But again, what we have here is a linear approximation of this vector valued function at the point omega naught. And then we did the same thing for matrix input functions. Here we have a double sum over all these partial derivatives, and we figured out that we can rewrite everything again as an inner product of the gradient and the perturbation. What changed is the definition of the inner product. When you have matrices, the inner product between two matrices is given by, you can say, trace of the first transpose the second. Slightly easier way to understand it is this, which is just a pointwise multiply of the first times the second, after which you sum up all the indices. Okay, so that's the inner product that we're using here, but otherwise, you see there's a common theme that the approximation of j at the point 0 is this constant term plus the inner product of the gradient and the deviation. Okay, and then on this page, we convinced ourselves using this first order, or using our Taylor series approximation, we convinced ourselves that in fact, yes, the gradient really is pointing in the steepest direction uphill, and the norm of the gradient really is the how steep it is at that point. And what else did we do? We finally did a little example of a matrix valued function, and we went through the steps of computing the gradient, which ended up being this outer product. So it's a column vector times a row vector. And we found that the linear approximation was equal to the original function, which makes sense because the original function was linear. And if you do a linear approximation of a linear function, you just get the same thing. So that was just a little example. And the last thing is we coded this in Python. And this is a really important thing here that we did. It's going to be really useful in some of the later labs, so I wanted to focus on this again. So in Python, when you have a vector, it's neither a column vector nor a row vector. In MATLAB, it is. In MATLAB, when you have a vector, when you construct it, you either construct a row or a column vector. But in Python, it's just a one-dimensional list. It's neither column nor row. So if you want to do something like this, where you have a column vector times a row vector, you have to give Python this, or NumPy, this extra information that you want the first one to be a column and you want the second one to be a row. And then you want to multiply them. And the way that you do that is you do that using this notation here. So we're starting with, in this case, A. You can think about this as a one-dimensional quantity. And we're sort of telling NumPy, think of this as a two-dimensional quantity where you keep the coefficients of A and you imagine them going down the rows. And then you sort of expand, you just copy, this is sort of the visualization of what's happening. This is your original vector A, and now you're just, with this none, you're saying copy as many columns as you need for the next computation. So this comma none expands it this way. And then with B, if you do it this way, you're saying keep the original coefficients going along the columns, and then copy the rows as many times as needed. So it does that. And in this example here, which this is just a screenshot from this Python broadcasting documentation, it happens to be an addition that we want. We want to add that column vector to this row vector. And what we mean by that is expand both of them so that they have the same dimensions, and then add those things. Okay. What we're doing here is not an addition, it's a multiplication, but it's a very similar idea. It's basically, it's allowing you to make this quantity an m by 1 quantity here instead of just a list of m numbers, and make this into an 1 by n quantity. And now that we've done that, we can multiply them, and it's going to be this column times row, which gives us the whole matrix we want. Okay, so this is a super useful trick. It's called Python broadcasting that does this. All right, so this will be really important in some of the later labs. Any questions? Yeah.
How does it distinguish between matrix multiplication and
Point-wise multiplication.
By the operator you use. So, so that's a great question. So let's look up here. So when we compute this, you can see that this is going to be a matrix multiply between matrix W and, we can think about it as a matrix B. Okay, and to do that, it's W dot B. So in Python, matrix multiplication is written by dot. It's the opposite of MATLAB, right? In MATLAB, when you do pointwise, you do dot star. It's the opposite. So here you do this WB, and now you get a vector. And now you want to do, let's say, and we'll call it C. A transpose C, where you computed C here, you do A dot C. Okay. Down here, you want to do a pointwise multiply, and now you're going to use the star. And that's going to do a pointwise multiply of that times that. But as you can see, you know, the addition, the dimensions, it's critical for it to understand that the first one is a column and the second is a row. And that's what we do with the none stuff. Yeah.
So what if we have row vector and then column vector? First the row vector. So the answer
If we
is
had-
supposed to be a scalar quantity, right?
If we had a row and a column,
Yeah.
I think it would essentially give you the same result because it's just doing a point element-wise multiply, and it's going to, yeah, I believe it's going to expand them as needed to do that.
Shouldn't we be getting a scalar quantity?
You would get a scalar if you did this dot product. So the dot, because remember that in a dot product, you do pointwise multiplies and then you sum them all together, right? Whereas here, there's no summing altogether. It's just the pointwise multiplies. So I think that's the difference. Yeah, so if you knew that you wanted to do this, you would do A dot B using that notation. Because that is really, that's a vector or matrix multiply, right? So we use dot for that. Okay. All right. If you ever find yourself like unsure, I would say just, you know, open up a little Sally or Jupyter notebook, create a couple vectors, like small dimensional, 2 or 3 dimensional vectors, and try stuff. Print out what happens. You'll immediately see what's going on. It's probably the easiest thing to do. Okay, any other questions? Okay, yes.
Couldn't we use the dot for this AB number?
Could,
Because it's matrix multiplication.
it's a good question. I don't know if it would work or not.
There's a function that's just for matrix multiplication. It's matmul.
Yeah, I mean, there's in Python or NumPy, there's different functions that do the same thing for sure. So it's something you could try. Yeah. Yeah. There's often multiple ways to do the same thing. Okay, so all right. So the next thing to talk about is using the gradient to do optimization. Before we get there, let's talk about just a few other sort of important miscellaneous things. So we've been focusing on the gradient going to 0 at the minimum of a function, but it actually goes to 0 at other places as well. We should be aware of this. So here's like one function where you can see that there's a peak here. At this point, the slope is 0. There's a maximum there. There's a minimum here. Slope is 0. So when you set up this equation and try to solve for W, you have to be aware that in some cases, you could get a minimum here. In other cases, minimum, you could get a maximum. And there's even another thing that can happen, which is a saddle point. In 2 dimensions, here's one way to visualize the saddle point. So this point right here has a 0 slope in all directions. What's happening is there's positive, well, you know, the function is curving down in one dimension, curving up in the other dimension. But that's not the only way it can happen. Here's another case. This is called a monkey saddle, where right here in the middle, the gradient is also 0 in any direction. So there's basically 3 types of points. When you think what W can cause this, there's 3 types of points. There's minimizers, maximizers, and saddle points. So we have to be a little bit careful. Just realize that. In any case, it's often the case that we can't just explicitly solve for this. Homework problems you can, things like that. But in practice, rarely can you do this. And for example, we said that logistic regression is this cost function we'd like to minimize. It's sort of the theme for this unit. And that's a case where we can't explicitly find the W that minimizes it. So instead, we're going to use a numerical approach. And this approach there's many variations of this, but the simplest one is called gradient descent. So this is how most machine learning objectives are minimized. So it goes like this. So let's say we're going to call J the thing we want to minimize, our cost, and we want to find the W that is the minimizer of that. We'll call it W hat. Sometimes people call this the objective, the cost, the loss, different terms. We're also going to assume that we are not going to place any constraints on W when we minimize it. For example, we're not going to say the coefficients of W have to be positive or something like that. So what we're doing now is called unconstrained optimization. We will briefly talk about constrained optimization later. That's a more difficult problem, so let's just focus on the simple one for now. And we're also going to assume that this gradient exists at all points. In other words, we can compute it. The function is differentiable. And if not, then you have to make some adjustments to some of the procedure. But we're going to take the simplest case. So this is the kind of workhorse algorithm here, gradient descent algorithm. So it goes like this. You start at some initial guess, call it W0, and then you iterate these steps until you reach the bottom. So what you do is, K is going to index the iterations, so we're going to start K equals 0, and then K equals 1, K equals 2. So the next K equals the previous K minus a small number alpha, small positive number, which is called the step size, times the gradient. Okay, so the key point here is gradient. Remember, gradient is uphill. Minus means it's pointing in the opposite direction. It's going downhill. And this alpha k means take a small step downhill. So it says just iteratively start somewhere, take a small step downhill, take a small step downhill, take a small step downhill, repeat until you get to the bottom. That's the approach. So here's a visualization. Perhaps we start here. We take a small step. So if these are equal cost contours here. If you take a gradient step, it's always going to be perpendicular to the contour at that point. So this is perpendicular, right? Notice that the direction we're moving is not in the direction of the minima. It's generally not. It's going to be some other direction, but the important thing is you are going downhill. We've made a little progress in going from here to here. Now we're closer to the bottom. Now we're going to take a gradient at this point, which is going to be in this direction. But can you see why we need to take a small step? What happens if I take too big of a step?
You're going to miss by a lot.
Yeah, I'll overshoot, and maybe I'll come over here, and maybe I'll just be farther away than where I started. Maybe I'll have a higher cost, trying to minimize the cost. So it's important to take a small step, and we'll see this mathematically in a couple slides. But that's essentially the approach. We take these small steps, and each time we move a little bit in a better direction, closer and closer. And another thing you can see is that the size of the step, if you fix the alpha and just say that alpha is like a fixed number, fixed small number, then the overall amount you're moving is also going to be related to the norm of the gradient, right? If you have a very big gradient, you're taking a very big step. So what's happening here is that this is a bowl which is shallower in the middle than, because it's quadratic. So it's steeper on the edges. So originally you take bigger steps. As you get closer to the center, you take smaller and smaller steps. That's just how the gradient works. So, but eventually, if you take enough steps, asymptotically, you get to the bottom. Okay, so that's the algorithm. There's many improvements you can make to this, modifications to make it faster. But at the end of the day, this is how all these algorithms are working. When you train a deep network, you're essentially running some special version of this with a few bells and whistles that try to make things faster. So take small downhill steps until you reach the bottom. That's the main idea. Any questions on this? Is this making sense? Yeah,
Does this always work?
it's a great question.
You mentioned maximum
Yeah,
points.
that's a great question. So I'm going to answer that in the next few slides. Was there another question? Yeah.
So is the gradient often determined numerically instead of like?
Yes.
Okay.
Exactly.
So you'd actually like just take a couple values around your point and then determine the gradient from that? Or?
That is a possibility, but ideally you can compute it. Like you have an expression for the gradient, you can program it, and you can plug in this number into that function, and it returns this vector. So that's what usually we have and usually we hope for. But yeah, it is possible to do a numerical approximation if you need to. Another question?
What is the relationship between the stuff on the previous slide about gradient zeros getting you not necessarily minimum and function being convex?
Oh, sorry. So here there's no convexity, but let's see. Are you talking about a different slide? Oh,
Yeah, that's the slide I was talking about. I just,
Oh.
because we had talked about how the gradient is 0 at minimum is that for convex functions or like, is there?
oh, okay, yeah. So we'll talk about convexity in a couple slides, but I think the main point of this slide was to realize that this idea of just computing the point at which the gradient goes to 0 can get you different answers. It can find you minima, maxima, or saddle points. So, maybe one thing to mention about this, if you use this procedure, could you ever converge to a maximum using this? What do you think? No. This is going to go downhill, but you could get stuck at a saddle point. This could take you to the saddle point at which the gradient becomes 0, at which point this says you're never going to leave. So it is theoretically possible. In practice, what happens is you don't really get stuck exactly at a saddle point. That's almost impossible to do, but the saddle point will slow you down. It will you'll slow down, you'll take really small steps, and eventually maybe you'll get away from it and you'll go further downhill. So saddle points can be an issue with these algorithms in terms of slowing them down. And then to come back to the question about convexity, I think I'm going to talk about this in a couple slides, but yeah, when you have convex functions, you don't have to worry about any of this. You don't have saddle points to worry about. You don't have, but we'll talk about that in just a few slides. Okay, was there another question or no? All right, any other questions? Okay, so so there was a good question about like, does this always work? So on this slide, we'll try to show that if your step size is small enough, then what happens is you can guarantee that you will converge to at least your closest by minimum. So let's see how this goes. So we learned before about this Taylor series expansion. So when we saw it before, we called this W naught. Now let's set the reference point at WK, which is the kth iteration of gradient descent. Furthermore, let's set this W at the next iteration, K plus 1. Okay, so I'm just going to plug in K plus 1 here, here, here. Right? So we get that. So this is still the Taylor series where we have the big O here on the norm. Now, if we're doing gradient descent, then notice that this has a very particular form. If I move this to the other side, or let's say if I move this here, that's just the gradient descent equation we saw, right? So that means that this difference, which happens there and there, I can plug in that function. And so that will give me, so we get this minus alpha k shows up here, and then this, we have the gradient. And then over here, we're going to plug this thing into that norm. And so if I have this minus inside the norm, that doesn't change it. I can just remove that, right? Because the norm is measuring the length. And furthermore, we can move the alpha k out of the norm, at which point it will get squared. So we get this. And so now the norm is just going to be applying to the gradient itself. Okay. One final simplification is notice that this is also the gradient norm squared. So we really have the gradient norm showing up a couple places. And then finally, let's pull this constant out of the order expression just for interpretation. So we have this fixed thing here, and then we have this order alpha k squared term. And remember, the way we interpret that is this is some number. We don't know exactly what it is, but we know that when alpha k is small, that number is less than or equal to this is, I'll write, for some c, for some positive c. It's less than or equal to c times alpha k squared for some positive c. And so now, let's sit back and reflect, what have we found? Why is this important or useful? So what we're trying to see here is, what is the cost after we take the gradient descent step relative to the cost before? So what do we want to happen? We want that this is lower, right? We want the cost to decrease. So does this second term help the cost decrease? Yes, because we said alpha k is positive. The norm must be positive or at least non-negative. And we have a minus. So overall, this is going to be negative or in worst case 0, so it's helping us decrease the loss. What about this term? Is this helping?
No.
No, this is hurting us. So here's the problem. If this term overwhelms the second term, we're in trouble because now the loss has actually increased. Right? So the key to say that gradient descent is actually going to work, we have to make sure that at every iteration, this overwhelms this, so we actually make progress. Of course, if we finally get to the gradient, to the minima exactly, or a saddle point exactly, then this will be 0, and we'll just be stuck. We'll never move. But as long as that doesn't happen, we'll be making progress. Right? So the key point now is, how can I guarantee that this term overwhelms this term? Well, they both have the norm gradient, so forget about that. Let's just focus on how can we make sure that alpha k is bigger than this order alpha k squared term. Well, remember that this can be interpreted as this. So how can we make sure that alpha k is larger than this? Any
C.
was it?
Decrease the value of c.
No, so c is a fixed number. We don't know what it is. It has to do with the curvature of the function. But let's say there's some c out there, some number. So how can I, but we have control over alpha. We can choose our alpha. That's part of our algorithm.
Alpha greater than 1.
The ABS less than 1.
Okay, so what if c is 10?
Less than.
What if c is 10? And I choose alpha as 1. So now I have minus 1 and positive 10. So this will overwhelm this. So that's not quite enough.
Choose alpha very small so that the square overwhelms the.
Yes. Exactly how do we do it, though? There's a particular choice of alpha. It has to do with c. 1 over c. If alpha is is smaller than 1 over c, then this is going to be c times 1 over c squared, right? Which is 1 over c. And, well, yeah. So basically, if alpha is less than 1 over c, maybe you can see this c will cancel the c squared. And when you square something, remember, it gets even smaller. So basically, by choosing alpha k less than 1 over c, you're guaranteed to make this smaller than this. You're guaranteed to make progress. So the point is, as long as you choose your step size small enough, gradient descent will work. If for some reason you run it and you see gradient descent is not working, it's actually going wrong, is increasing, then you say, oh, I got to decrease my step size. We will, in probably not this lecture, next lecture, we'll figure out there's a sophisticated strategy we can use to adapt this alpha on the fly to always make sure that it's small enough. So we can do that, but the more, the simpler approach is you just choose a fixed alpha in advance and you just choose it really small. And usually that works too. Maybe it's slow, but it will work.
So here we assume that the alpha should be 1 over like c.
Yeah,
Or
so,
less than, I mean, 1 over c. But we don't, so this c is, itself is like upper bound of that, because we said that this big O of a k, alpha k to the power 2 should be less than c square a k. So we don't know c. We should like find the upper bound of the c in order to
Right.
like this as step size.
yeah, we could, exactly, we can do that algorithmically. So we'll see that there's a procedure, it's called Armijo's rule. It's a clever way of figuring out, kind of like figuring out C. Figuring out something about C that guarantees that for this alpha, it's going to be small enough to guarantee progress. So that's what we'll do, yeah. We can choose alpha, we can't choose C, but we can figure it out as we go. And it has to do with the curvature of the function, basically. It's like the steeper the function is, you know, like if the function is really steep and you choose a big alpha, as we saw before, you shoot to the other side. That's bad. That's what you don't want to happen. If the function is shallow, it's probably, or not, if it's not so curved, it's probably not going to happen. So the steepness kind of, the curvature matters in some sense. Okay, great. So, so the whole point of this is basically to say that if you choose your step size small enough, gradient descent will work. You will get decrease in your cost at every iteration, and that's really what we want. Okay, answer your question? Okay, great. Any other questions? Okay, cool. So now let's also realize that there's another problem we haven't talked about yet, which is the fact that in practice, we could have a function that has several minima of different qualities, like different heights. So in this picture here, we see that this is really truly the minimum of this function, you know, maybe everywhere. And this is what we call a local minima. So it's the minimum, you know, over some region, but it's not truly the global minimum. So this is another issue that arises in optimization problems. Maybe not all optimization problems, but it can happen. It's definitely an issue with deep networks, as we'll see. But there's a case in which it's not an issue, which is when we have a convex function. So we're going to define them carefully, probably in the next lecture, not today. But I just wanted to say that the nice thing about having a convex function is you do not have to worry about global versus local minima. You do not have to worry about saddle points, all that stuff. You can be assured that when you take an approach like gradient descent, that it will find a minima. Maybe the minima is not unique. Maybe you have something like this, where there's many equally good places. It will find at least one of them. Okay, so we'll talk about the details later, but I just wanted to point this out. And I don't know if you remember, but so far in the course, we've focused on two loss functions, right? RSS and logistic loss. We also saw, yeah, there's like multinomial logistic regression, binary, right? All of them have been convex. So for all the stuff we've seen before, these approaches, these gradient-based approaches should work. Without a question, they're not going to get stuck in some bad local minimum. When we get to neural networks, however, then the situation changes. Then you have to use algorithms which are somehow clever enough to avoid the bad local minima. And there's all sorts of techniques that these algorithms use to do it, but and you never are quite sure if they've done it, but in practice it does seem to work. But anyway, so we'll talk about that stuff when we get to those topics in units 8 and 9. But for now, so far in the course, we've focused on these convex functions. So we just want to be aware that this stuff happens in general, but doesn't happen for convex functions, so we don't have to worry about these problems. Okay. All right. Good. Any questions so far? All right. Okay, so we're finally in a position to come back and apply the tools we've learned about to sort of the demo or the goal of this unit, which is to figure out a way to minimize this cross-entropy loss, which is what we saw in binary logistic regression. And we're using the specific version where the labels are 0, 1 versus 1 and minus 1, just because it's a little bit easier to look at. But either way, it would work fine. So our objective is to find the W that minimizes this. And as we said, this turns out to be convex, which is great because we don't have to worry about gradient descent getting trapped in a local minima. It's also differentiable everywhere, so we don't have to worry about derivatives not existing. But as you can see, it's kind of complicated. So first of all, let's look at the way it's written. So the thing we really want to adjust are the W parameters, but all this stuff is actually defined in terms of the Z's, the scores, and the scores are related to the W parameters in terms of our features. So it's a bit complicated. So let's think about how we can organize things in our mind. And so the way that we want to think about this is really this cost function J is a composition of two simpler functions. The first one is a linear transformation. And I'm saying it's simple because it's linear. Linearity is simpler than nonlinearity. We know very well how to deal with linear functions. Then we have a separable function. So let's see how this works. So this first function, I'm saying, is a function that takes W to Z, to our scores. So this is what happens with the ith score, right? And this is our W. And if we stack all our scores together into a column vector, Z1 all the way to Zn, then you get a matrix. Sorry, this is a 1 all the way down to here. And this matrix, we've always called this the A matrix. Okay, so basically, and we've called this vector here, this is the Z vector. So that's where we get this Z equals AW. And I'm just writing this explicitly. I'm saying think of Z as a function of W. Okay, then, once you know the Z, this function is simple in the sense that it's separable, meaning the overall function works element-wise on the different components of the Z vector. So, in other words, you can write this as a sum of functions Fi, where each works on the scalar Zi. Okay, so both of these are simple in some sense. This one is simple because it's linear, but complicated because it takes a whole vector of parameters to a whole new vector. In other words, there's all these like cross things that are happening, right? Every one of the W's affects all the Z's in general. The second one is simple in that all we have to do is look at each Z separately. We don't have to look at all the Z's together. But it's complicated in that it's this nonlinear function. It involves natural logs, exponents, and so on. But by thinking of the overall J, which is complicated because not only does it mix together all the variables and have nonlinearity, we've split it into linear, separable. And so basically we can think overall of J as a function of W as first going from W to Z and then going from Z to F. And this is a really powerful approach for general machine learning problems. It's sort of like a divide and conquer approach where you split a complicated thing up into simpler sections and you understand each section individually, and then you can put the sections together when you're done. And often to do that, you have to use what's called the multivariable chain rule. So this is going to be a huge thing we're going to use when we talk about neural networks, but we're already going to use it now. And it basically tells us when you have this sort of cascaded thing where W affects Z, which affects F, and you want to take the derivative of, you could think of it as J with respect to W, or you could say F with respect to W, sort of the same thing. You have to think about all the intermediate variables that have an effect. So maybe one way to do this is to draw a little diagram which explains sort of conceptually what's happening. So it's like these are the W's here, these are the Z's, and then this is F or J, either way you want to think about it. So this linear part, you can see that all the W's affect all the Z's, right? That's how it's complicated, but it's linear. And then the second part, you can see that all the Z's affect that single F or the single J. So now the way to understand this multivariable chain rule is if you want to look at how, let me change colors, how this is affected, let's say, by one of these guys, you have to think about all the different ways that it can affect it. So there should be one there. So, for example, this W can affect F or J through that Z, or through that Z, or through that Z. So there's many different paths, and this summation is basically summing across all the different paths. It's saying, okay, df dwj is going to be a sum across all these different I of df dzi, so one of those, times dzi dwj. Okay. Does that make sense, what this is saying? Okay, so that's a way to think about it. So for this particular problem, we need to know, these derivatives. So what is df is dzi? So as you can see, that's, okay, so here's our F equation. So remember that when you differentiate through the natural log, you get 1 over. So you get 1 over this. And then you have to differentiate the inside. When you differentiate exponent, it doesn't change. You just get EZI. And the second term, dFi dZi is just YI. There's a way that we can simplify this. We can basically multiply top and bottom by e to the minus zi, which will cancel this, and put a minus e minus zi there. So that way we only have one exponential to deal with instead of two. Now the second derivative we have to consider, this stuff. This is actually pretty easy, right? Because remember this equation here. So this is z equals aw. We can rewrite that as zi is a sum over j, aij, wj. And so now you can see dzi dwj, or maybe if, again, sometimes I put primes here just to not confuse this j with those j's. So if I do dzi dj, dwj, only one term in the sum is going to matter. It's the term where j prime matches the j. And at that point, the only variable left is this, or the only term in the sum is this, and so I do d of that, dwj, I just get aij. Does that make sense? Okay, so that part is easy because it's linear. This part is easy because it's scalar. Okay, so finally we know how to plug things in here. Okay, so I'm actually, the next slide, I made some changes just this afternoon to try to explain it better, so let me skip ahead to that version. Okay, so so in principle, you can see we have the ingredients we need to compute these things to eventually get what we want. When we program this, as I said before, typically, not only do we want to compute the gradient, but we also want to compute the cost, because when we're doing our gradient descent optimization, we want to keep an eye on what the cost is, maybe plot it, see is this thing still going down? Do I need to run more iterations, or is it gone down enough that I can stop? So we want to do both. And typically the way that we organize our computations is what's called the forward pass and then the backward pass. The forward pass computes all the variables. So like essentially you start with a W. You have to first figure out what are the Z's that correspond to that W. And then finally, once you know the Z's, you can put them through F to get J. So that's the forward pass. You go from W to Z to F or J. Okay, so in this case, the first thing we need to do, take our W vector, take our feature matrix, do this matrix vector multiply to compute our scored Z. Second, we can evaluate F of Zi, which are all the terms that go into our logistic loss. And we saw that we have this equation here. Now to be efficient, we're going to try to massage this to make it look like some of the other things. Remember how this thing, we had this thing? Maybe we can compute this once and never again. And so I want to make this look like this. So what we can do is the following. Okay, so first of all, notice how I have a minus here. Remember when you put a minus in front of a log, that's like inverting the argument, right? Second, where did this come from? Well, this thing, minus log e to z, so this log cancels the e to give you a zi, so you have minus zi, but now I'm going to add plus zi to cancel that. Okay, so I've introduced this term, which cancels this. And again, the reason I'm doing this is because once I have things in this form, now you can see I can rewrite it like this, which means this is a quantity I can compute once, and then I can use that in the forward pass, but I can also use it to compute the gradients. So I'm just doing this to be efficient. Okay, so let's look at the code. So we have a function here. It takes in the W vector, the X matrix of features Y. So the first thing we're going to do is we're going to make our A matrix by computing or constructing a vector of ones, appending that to our feature matrix X. That gives us our A matrix. Then we do this A dot W, matrix vector multiply to compute Z. And finally, we're going to call this 1 over 1 plus e to the minus zi. We're going to call that py. You remember why we call it that? Because that's the probability that y equals 1 according to the logistic model. Okay, so we compute that. Now this is a vector of terms for all the different i's of this. And then finally, we can compute the rest of this. So we have this 1 minus y times z computes this. Notice that y and z are vectors, and this asterisk is a element-wise multiply. And then over here we have minus log py, which is minus log py. So that's j. So this is the forward pass. We computed z and j. Now let's compute the gradient. As you can see, if we're clever, we can do this in 2 lines. Let's see how we do that. Okay, so from the previous page, this is our multivariate chain rule. We said dj dw is the sum over I times df dzi, dzi dwj. We figured out that dzi dwj is aij. And we have an expression for this guy. We computed that on the previous page. But just to keep the notation simple, let's just write it for now as gradient of f, the ith index of the gradient of f. Okay, so this is the full gradient vector we want to compute. So these are its components. Right? These components are the things that we talked about how to compute. So I'm going to plug this in to the different components. But as you can see, this is like feature feature index 0. So I'm going to have a j of 0 up here. And then I go down and I increase j until I get to the dth feature. But in all cases, we have this sum. So this is like a dot product, right? It's a dot product between the gradient vector and one row of your A matrix. So let's expand that dot product into this times this. Right, that's what this is. And similarly, this guy is this times this. And now that we've sort of unfolded it like this, you can see that this is just the A matrix, but it's transposed. The first index, you can see this is constant as you go down here, right? That's not usually how it is. If you transpose this matrix, then it's the A matrix. So this is A transpose, and then this is just the gradient vector. So at the end of the day, we have a pretty simple expression for the gradient, which involves this vector of partial derivatives, these guys, this gradient vector here, and the transpose A matrix. Okay, so to build this in our code, that's easy because this is just py minus y. So that's our df dz vector. And then finally, to compute this, we do A transpose dot. That's A transpose times that vector. And that gives us our gradient, and then we just return them. Okay, so that's how you typically write code like this. You try to be efficient because in practice you need to run this code maybe thousands of times. And it does involve matrix vector multiplies. Sometimes those can be large. You have a large training data set, so you want to be as efficient as possible. Okay, so next thing to talk about is a few more coding things, and then finally we'll program it and see how it works. But I think this is enough for today. So we'll resume with this stuff next Monday, and Friday is the midterm. So please see me in office hours or see Kai-Ying if you have any questions on the material. And good luck studying. See you guys here on Friday.